the first topic of our computer network subject, which is concept of layering. So as part of this concept of layering, what we have discussed in our classes, we have discussed about reference models. And we know that there are so many reference models in the internet, but according to our education, purpose, we can see that there are only two reference models which are listed, like ISO-ASA reference model and TCP/IP reference model. So first, what is the basic difference between this ISO-ASA reference model and TCP/IP reference model? If we can see, so this is what the distinction between this ISO-ASA reference model and TCP/IP reference model. So it can be helpful to you with respect to theory-based questions like MCQ, MSQ kind of questions can be expected based on this table. So if you can see that the first parameter, which stands for, you know that OSI stands for Open System Interconnection, whereas TCP/IP reference model, where TCP/IP stands for Transmission Control Protocol and Internet Protocol. Then the number of layers, if you can see, it is having 7 layers. ISO-ASA reference model is having 7 layers, and your TCP/IP reference model has 5 layers. Then coming to organization that is introduced, okay, that is the ISO-ASA reference model, by which organization it is being introduced, in the sense, if it is ISO-ASA reference model, then ISO, which stands for International Standard Organization, and TCP/IP reference model is introduced by DARPA, which is Department of Advanced Research Project Agency Network. Next, the protocols. If you can see, ISO-ASA reference model is protocol independent, but whereas TCP/IP reference model is protocol dependent. Reason, if you can check the diagram of ISO-ASA reference model and TCP/IP reference model, your ISO-ASA reference model does not exhibit protocols, but your TCP/IP reference model exhibits the protocols, right? So that is why we are saying that it is independent and it is dependent. Next, approach. It is vertical approach. ISO-ASA reference model is following vertical approach, whereas TCP/IP reference model is following horizontal approach. So the meaning of vertical approach is, like, you know that in ISO-ASA reference model, the data transmission is traveling from application layer to physical layer and then entering into the channel, and then it is going to physical layer to application layer. So vertical approach it is, right? But when it comes to TCP/IP reference model, this is with respect to protocol conversation, like sender side TCP, receiver side TCP communication. But ISO-ASA reference model is speaking about this U shape, whereas your TCP/IP reference model is speaking about this horizontal line space, right? So protocol to protocol conversation, that is what your horizontal approach, whereas vertical approach is what? Layer to layer conversation. So from this layer it is getting the data, and then it is forwarding to the lower layer, and then it is going to again lower layer, then from lower layer it is going to upper layer, right? So that is what the meaning of vertical approach and horizontal approach. So coming to session layer and presentation layer presence. If you consider in ISO-ASA reference model, these two layers are presented, but whereas in TCP/IP reference model, we don't have that session layer and presentation layer. There corresponds to one layer, that is your application layer, right? Then coming to reference. So, but among these two reference models, which reference model is used as a reference to data transmission, in the sense ISO-ASA reference model is using as a reference, whereas TCP/IP reference model not, right? Then coming to flexibility. As ISO-ASA reference model is not exhibited the protocols, it is flexible, but TCP/IP reference model is rigid. Reason, it is exhibited every protocol with respect to corresponding layer. That is why it is rigid, but this is flexible. Current internet is following which reference model? So this TCP/IP reference model, right? That's what the meaning of usage is high here. Then standardization, ISO reference model is considering as a standard for data transmission, whereas TCP/IP reference model we are not considering as a standard. So overall, these are the points that are related to what are the various differences between TCP/IP reference model and ISO-ASA reference model. ISO reference model diagram. This is what your ISO reference model diagram. You know that if your sender system is being configured with ISO reference model, it is having 7 layers. And if your receiver system is also configured with ISO reference model, it is also following what? 7 layers. It is also having 7 layers of thing, right? Right. So then we are moving to the next. What is the next thing that we are going to see? Functions. Every layer functions we are going to see. Coming to the functions, physical layer functions are listed as follows like. So physical layer is providing the data format in terms of bits. That is what your PDU. PDU, which stands for protocol data unit, right? Protocol data unit, which is also in general terms that we can call it as data transmission, data format, that is supported by your physical layer is bits. It is also defining, physical layer is able to define transmission rate, right? So you know the transmission rate is also called as bit rate, data rate, transmission speed, bandwidth, channel capacity, right? So that is also we have defined how physical layer can define the transmission rate. It depends on the communication between the center physical layer and the channel, right? So the communication between the center physical layer and channel, we can say that physical layer is able to define the transmission rate. Then coming to transmission media. So transmission media is, you know that two types of mediums. See, generally transmission medium is what? Your channel, your link, right? So your medium, right? So which is also called as communication medium. So this is two types like guided media and unguided media. So guided media, which is also called as wired media, unguided media, which is also called as wireless media. Okay. So this transmission media, if you speak about exclusively wired media, we are having three types of medias. What are the three types of mediums? One is called fiber optics, another one is called coaxial cable, another one is called, you know, what is the other one? Twisted pair, right? So twisted pair, coaxial cable and fiber optics are the general wired medias that we are using to connect the systems or else to do data transmission between one system to another system. So how physical layer can define the transmission media, that is also we clearly defined in our classes that it is depends on the distance between sender physical layer and receiver physical layer. So depends on the distance between sender physical layer and receiver physical layer, we are able to see that the physical layer is able to define the transmission media. Then coming to transmission mode, you know that transmission mode, what way, in how many ways people are, I mean, two systems are communicating together, that is called transmission mode. So basically we are having three types of transmission modes such as simplex, half duplex and full duplex. So among this simplex, half duplex and full duplex, if we can see, this physical layer can also define the transmission mode, that is depends on the conversation between the sender physical layer and receiver physical layer, right? Then physical layer also defines the topology. So what is the meaning of topology? Topology refers to the physical and logical behavior of a network, right? It refers to the physical and logical behavior of a network. So here what is the meaning of physical behavior? How the systems are being interconnected. And what is the meaning of logical behavior? How the systems are communicating together. That is called logical behavior and physical behavior. So here topology, you know that how many types of topologies we have? Total 5 types of topologies such as bus topology, ring topology, star topology, mesh topology and tree topology. Among all of these, what we are doing, we are making them into two groups, that is bus topology and non-bus topology, right? So your physical layer can define the topology. How it is able to define, that depends on the level of physical layer with respect to all systems. And mind that this is explanation only with respect to theoretical, but not practical, because in practical all the systems are being connected. I mean, your network is being connected on the surface, so that it seems the physical layer is at the same level irrespective of the topology. But theoretically we can speak like, if all the systems are being connected in a bus topology, all the systems can have the physical layer at the same level. The explanation that I have given in our classes like this, right? So how I have given, please recall. So if you consider is what your bus topology, and all your systems are being connected to the same channel in linear fashion like this. Now, if all these systems are configured with ISO OSI reference model, we can have 7 layers here, like application layer to physical layer, application layer to physical layer, application layer to physical layer. So now this physical layer level with respect to all systems can have the physical layer at the same level. That's why we are saying that physical layer can define what type of topology we are using. That is depends on the level of physical layer with respect to all systems. In the same way, if you consider ring topology, this is what your ring topology. Just assumption, this is what your ring topology means. You can say non-bus topology. Here, if you can check all these devices, if they are configured with ISO OSI reference model, then this system can have physical layer here, physical layer here, physical layer here, and physical layer here. So if you can check, all these 4 systems does not have the physical layer at the same level. If you consider this is your nth layer, and this is going to be n plus 1, and this is going to be n minus 1. So like this, you can imagine in a theoretical manner. So depends on this, we can say that if all systems are having physical layer at the same level, if all the systems are having the physical layer at the same level, then we can say it is bus topology. If the systems are having physical layer at different level, then we can say it is called non-bus topology. So like this, we can define how your physical layer can define the topology, right? Then we are having encoding. You know that what is the meaning of encoding? Encoding, it means converting the digital bits into voltage signals, converting the digital bit into voltage signals, right? So we discussed, there are so many encoding techniques in the internet, but mostly we have discussed about 3 types of encoding techniques, like binary encoding, Manchester encoding, and differential Manchester encoding. Then coming to transport layer functions, the PDUs of the transport layer are segments. Transport layer can do flow control. So you know that flow control, how your transport layer can do flow control? Transport layer can do flow control using sliding window. But this sliding window is having a drawback. What is the drawback of this sliding window according to this transport layer? Silly window syndrome. It is having a drawback of silly window syndrome. So this silly window syndrome, to avoid this silly window syndrome, right? So what is the algorithms that we can use? What are the solutions that we are having to avoid this silly window syndrome? So we are having 2 types of algorithms. What are the 2 types of algorithms? One is called N-glass algorithm, and other one is called Clark's algorithm, correct? One is N-glass algorithm, other one is called Clark's algorithm. So these are the 2 algorithms that are used by your transport layer to handle this silly window syndrome. So where this N-glass algorithm we are using at center side, and this Clark's algorithm we are using at receiver side. At receiver side we are using it, and this is used at center side. Okay, right. Then coming to congestion control. So transport layer can handle congestion in how many phases? In 3 phases. What are the 3 phases? One is called slow start phase, other one is called additive increase phase, and other one is called multiplicative decrease phase. Right? So here additive increase phase, which is also called as what? Congestion avoidance, and multiplicative decrease phase, which is also called as congestion detection, right? It is also called as congestion detection, and this is also called as congestion avoidance, right? So you know that in the slow start phase, what kind of growth you can have, in slow start phase, what kind of growth you can have in your congestion window. In slow start phase, the congestion window can have exponential growth, right? But in the additive increase phase, what kind of growth you can have? What kind of growth we are having in the congestion window size in the additive increase phase? Linear growth, right? One segment gets added, correct? So, and in the multiplicative decrease phase, we have spoken about 2 cases. What are the 2 cases? One is called strong possibility for occurrence of congestion, and other one is called weak possibility for occurrence of congestion. What is a strong possibility for occurrence of congestion? After sending one packet, all the further packets also got lost. That is called your strong possibility for occurrence of congestion. What is the meaning of weak possibility for occurrence of congestion? After one packet is being dropped, some packets after the that packet, okay, some packets if you are transferred, they can be successfully reached to the receiver. Such kind of scenario is called weak possibility for congestion, right? So the strong possibility for occurrence of congestion we have considered as timeout, whereas weak possibility for occurrence of congestion we have considered as 3 duplicate acknowledgement. So just assumption, channel utilization is given greater than 90%. If you consider this is 100%, just consider this is 100%. Okay, then tell me what could be the answer here. A host in one organization is connected to another host in another organization using 1 Gbps link with 25 milliseconds of RTT. The network administrator of this network tuned the packet size of 1000 bytes to transfer large files optimally over this network. In order to have channel utilization which is greater than 96%, how big the window size is? Let's say in terms of packets. You need to express the answer in terms of packets. So simple, the question is given something like bandwidth is given, size of the data is given. So immediately what we can find out? Tx we can find out. What is the Tx? L by B. L is in terms of bytes, so that 8 into 10 power 3 by, it is Gbps 10 power 9. So, but here it is given 25 milliseconds, no? RTT is given in terms of millisecond, better express this is also in terms of millisecond. Okay, so how can I express this in terms of millisecond? 8 into 10 power 3 by 10 power 3, 10 power 3 and 10 power 3. This 10 power 3, this 10 power 3 cancel. Okay, and then this I can write as 0.008 milliseconds. Yes or no? Tx is 0.008 milliseconds. Right. So now, as the question is given, efficiency is 100% or else more than 96%. You know that the bandwidth delay product. What is the bandwidth delay product here? So bandwidth delay product is B into RTT. What is the bandwidth here? 10 power 9 into RTT. What is the RTT value? 25 milliseconds. 25 into 10 power minus 3. Then you are getting 25 into 10 power 6 bits. This is in terms of bits because this is 1 Gbps, no? Right? This is bandwidth delay product. So you are able to place these number of bits onto a network. Let's say this is your number of bits that you can place onto the channel. Now, if you want to find out the packets, then what you have to do, simply divide this 25 into 10 power 6 by packet size. What is the packet size? 1000 bytes, right? But this numerator is in terms of bits, so consider this is also in terms of bits. So 25 into 10 power 6 by 8 into 10 power 3. 25 into 10 power 6, 10 power 3 gets cancelled. So 25,000 by 8. So you may get something like 3126 or something you may get, right? So what is the close answer to that question? So it is option C you can consider. Closely, it is very close to that, right? So that's why option C can be the answer for this question. But if you strictly take 96%, strictly you can take 90%, then answer could be option B. Because I consider as is 100%, then I consider I am getting this option C. Okay. If you strictly consider 96%, then you can have option B maybe. Okay. Yeah. So switching, a small content is there, switching. You know that what is the meaning of switching? Process of interconnecting the switches is called as switching. So since you are connecting the switches, you are forming a switched network, and this switched network is two types: connection oriented switching and connectionless switching. Yes or no? So that connection oriented switching example is circuit switching, and the connectionless switching is your packet switching and virtual circuit switching. So here the most important thing is circuit switching and packet switching. So why we are considering most important, why we are saying that these are the two switching techniques are important, because we regularly habituate with telephone networks where we are using circuit switching. We regularly habituate, work with internet where we are using packet switching. So your packet switching we are using in internet, and your circuit switching we are using in the telephone networks. So since we are working mostly with these two types of networks, we consider the most scenarios we are considering only these two networks, switching networks, circuit switching network and packet switching network. Are you clear with me? Right. So then look at the basic differences between this circuit switching and packet switching. Circuit switching, it is a connection oriented switching, I told you. So that connection setup is required. But packet switching is connectionless switching, no? There is no connection setup requirement. Dedicated physical path, yes, in circuit switching you require dedicated physical path. The reason you are establishing the connection between the sender and receiver. So since you are establishing the connection between the sender and receiver, obviously the path is going to be very dedicated to that sender and that receiver only, because before doing the data transmission, the resource reservation is happening in the circuit switching in a static manner. So before doing the data transmission, you are reserving the resources, so that whatever the resources that are involving in that path between the sender and receiver, whichever path you have established, in that path whatever the resources that are involved, like switches, switch buffers, link bandwidth and etc., they're all being dedicated between that sender and that receiver only, not other sender and not receiver. That's why the path is dedicated, physical path is happening in the circuit switching but not in the packet switching, because in the packet switching the resource reservation is dynamic. Each packet follows the same route. Yes, in circuit switching the packets can be traveled in the same path, because you know that the path is being established between the sender and receiver, and that is the first packet can have header, the first message can have header, so that all the messages can travel in the same path in which the circuit is established between the sender and receiver. But in the packet switching, packets can travel in different paths. Reason, the header can be appended to every packet here, but in the circuit switching the header can be appended only to the first packet or else first message, so that all the messages can travel in that path only. But here every packet can have the header. In the packet switching, every packet can have the header. So since everybody knows the destination, they can travel in different paths. But in the circuit switching, only the first message will have the header. Okay, so that all the packets will travel the same path. Which path? The path that is established between the sender and receiver before initiating the data transmission. Okay, that is what the meaning of this third parameter. Then packets arrive in the order. Yes, in the circuit switching, packet can be arrived to the receiver in the order. But whereas in packet switching, packets are arriving in out of order. Reason, the packets are being traveling in multiple paths. Since every packet is having the destination address, the packets will travel in their own paths, but not in the same path. So that in packet switching you can have out of order delivery, but in the circuit switching you can have in order delivery. Next, is a switch crash fatal? So switch failure is a problem? Yes, in the circuit switching it is yes, but not in the packet switching. Reason, in the packet switching, okay, in the packet switching, even though one a switch is failed, the packet may take to another switch, because it is dynamic resource reservation. But here the resources are being reserved in a statical manner. Before doing the data transmission, all the switches you are reserving. So among the reserved switches, if any switch got failed, you are stopping your transmission. The data does not have any alternate way to travel because that is a dedicated path. So that is why the switch crash is a big fatal in the circuit switching but not in the packet switching. 100% bandwidth availability is possible in the circuit switching but not in the packet switching. Reason, static resource reservation. Time of possible congestion. Yes, congestion is possible in both circuit switching and packet switching. Okay, in both circuit switching and packet switching we can have congestion, but in the circuit switching where the congestion is possible at the time of setup. It means, you know that I told you this point clearly. This circuit switching we are using in the telephone networks. So in the telephone networks, you are having an office, a small office called PSTN, Public Switching Telephone Network Office. PSTN office is there. To that PSTN office, everybody calls can go, and everybody is requesting that PSTN that please connect my call to my receiver, please connect my call to the receiver. All the call, my call, a neighbor's call, and your call, everyone's call can go to the PSTN office. And everybody is requesting connect my call first to the PSTN. So that is where the congestion is possible. That is what at the time of setup. But in the packet switching, on every packet, it means the packets are maybe travel in different paths, because it is a packet switching, and in the packet switching, every packet is having header so that they can travel in one paths, so that every packet can involve in the congestion. There is a possibility for every packet can involve in the congestion. So that is why we are saying that on every packet there is a congestion is possible. Next, potentially wasted bandwidth. Yes, bandwidth wastage can be happen in the circuit switching. Reason, once your circuit is established, it means once you have reserved the resources statically, if you are not doing any data transmission, if there is no data transmission after the circuit is established, if there is no data transmission between the sender and receiver, then what does it mean? What does it mean? There is no data transmission between the sender and receiver. What does it mean? The resources are getting wasted, right? The resources are getting wasted. But in the dynamic resource reservation, whereas in the packet switching, you are finding the dynamic resource reservation. It means that if one switch is not working, the packet can go to the next switch, next path. So that is why we are saying that bandwidth wastage can be possible in the circuit switching when after the circuit is established, if you don't do continuous data transmission. If you are not doing continuously data transmission, then bandwidth gets wasted, and that is what the drawback of even this circuit switching. But in packet switching it is not, right? Because the packets are traveling in multiple paths. In those paths, if any switch is failed, it can go to the next path, so that the resource effectively can be utilized in the circuit packet switching but not in the circuit switching. Store and forward mechanism. Store and forward mechanism or else transmission you can see only in the packet switching but not in the circuit switching. In packet switching, whatever the switches that are being involved, those switches are routers which are having store and forward behavior. But in the circuit switching, the switches does not have store and forward behavior. They just have forwarding mechanism. Circuit switching is transference, but now this packet switching is not transparent, right? So what is the meaning of this transparency? You are creating the path, you are establishing the path, right, before doing the data transmission. It is very transparent, and then the messages are being traveling only in that path. But in the packet switching, you are not doing any connection establishment, you are not doing the resource reservation in prior to data transmission, but your receiver is receiving the message. So I don't know how the message is being reaching to the receiver, but my message is being reaching to the receiver. But in the circuit switching, it is clearly defined, like first circuit is established, through the circuit the packets are being traveling and the receiver is receiving it. But such kind of transparency we cannot see in the packet switching, and at the end in the packet switching the receiver is able to receive the message. But how That we cannot see. That's why we are saying that packet switching is not transparent, but circuit switching is transparent. Then charging. Charging means what? Cost. So as you know that the circuit switching is using in telephone networks. In the telephone networks, if you can see the postpaid bill statement, in these number of minutes you have spoken, these number of minutes you have used my teleservice, so that per minute you have to pay this much amount. So like that, in olden days we used to have per minute we used to have 1 rupee, 2 paisa, like that. At the end Jio came and then it made it is 0 paisa. Are you following my point? So that is the way. So that is what per minute in the circuit switching you can have charge. But when it comes to the packet switching, it is per packet. It means, you know that the packet switching we are using in the internet. So since we are using it in the internet packages, if you can recall, your home is having Wi-Fi connection, you might be subscribed to 30 Mbps speed, 10 Mbps speed, yes or no? That is called, per packet. So like this you can distinguish what is circuit switching and what is packet switching. So I hope you are clear with this. It is clearly mentioned that 3 cases are there. In the first case, a single packet containing the complete file is transmitted from A to B. So case 1 if you consider. Case 1 if you consider, your message is not breakdown here. So file size is 10 power 3 bytes. Let's say data portion is 10 power 3 bytes. And bandwidth of the link is given 10 power 6 bytes per second. Bandwidth is given 10 power 6. So case 1, bandwidth is given 10 power 6 bytes per second. File size D is given 10 power 3 bytes, and it is clearly mentioned each packet can have header 10 power 2 means 100 bytes of a header. You know that it is a packet switching. So for every packet you are appending the header here. So that what is the header size that you are having here? 100 bytes. This is 1000 bytes, this is 100 bytes. So overall, what is the size of your message? 1100 bytes. And the question is asking you about to find out only, consider only the question is clearly mentioned. Consider only transmission time and remaining everything. So if I consider only transmission time, that is if I calculate the Tx now, that is L by B. This is 1100 bytes and this is 10 power 6 bytes per second. So bytes cancel, 1100 microsecond. But here this is the network, no? So you have A, you have router R1, you have router R2 and you have B. Then what is the total time formula you have? X into Tx plus Tp plus x minus 1 into what? Tproc plus Tq plus n minus 1 into Tx. This is the formula you have. But here all are being 0 except Tx. So this is 0, this is 0, this is 0. Right? So n minus 1 number of packets is 1 here, right? N is equals to 1. So that this is also going to be 0. So overall x into Tx. What is the x? How many hops you have? 1, 2, 3. 3 hops. So 3 into Tx. What is the Tx? 1100 microseconds. So overall you are having 3300 microseconds. This is what your T1 value, first case. Then coming to second case, case 2. Case 2. Bandwidth is 10 power 6 bytes per second. In case 2, what you are doing? The file is split into 10 equal parts. 10 equal parts. It means n value is given 10. N value is given as 10. N is given as 10. So your file size is 1000 bytes, and if it is being divided into 10 equal parts, 10 power 3 by 10, 100 bytes. Every packet is going to have 100 bytes of data. And for every packet you are appending header of 100 bytes. So overall your L is now how much? 200 bytes. Yes or no? So then Tx is equals to L by V. So 200 by 10 power 6. So 200 microseconds is your Tx. Then substitute this formula. X into Tx. X is what? Number of hops. Number of hops are 1, 2, 3. 3 hops. So 3 into, you can say 3 into total time is equals to 3 into 200, which is 600, plus n minus 1. What is the n? 10. 10 minus 1, which is 9. 9 into 2, 1800, which is 2400 microseconds it is. This is what your T2 value. Right? Your T2 value is 2400 microseconds. Your T1 value is 3300 microseconds. Yes or no? Then, if you consider T3, case 3. In case 3, same bandwidth is same, but n is what? The number of packets is what? You please verify. In the third case, the file is split into 20 equal parts. 1000 bytes by 20. 1000 bytes by 20. 1000 by 20. How much? 50. Right? 50 plus header size is 100. So that your L is what? 150. Your L is 150. And your N is what? 20. 20 equal parts. And Tx is equals to L by V. L is what now? 150 na? 150 bytes, 10 power 6. So 150 microseconds. Yes or no? 150 microseconds. So 1000 by 20, 50, right? 50 plus 100. 100 is the header. 150. So 150 microseconds is your Tx. Right. So then the same formula now substitute here. So if I write here total time, 3 into Tx, 3 into 150. 3 into 150 means 450 microseconds plus n minus 1. How many packets you have? 20. So 19 into 150. 19 into 150. So what is this value overall? If you can evaluate this expression, you will be getting 3300 microseconds. This is what your T3 value. So overall, your T1 value and T3 value both are same. T1 is equals to T3 and your T3 is greater than T2. This is what you can see, that is your option D. So like this you can answer this question. I hope everybody is clear with this explanation. Simple formula. This formula is enough to solve any question based on your packet switching content. So this is the question. I mean you solve now these questions in previous year papers. So what is the solution? Transmission rate at the center is given 80 kbps. So bandwidth of the center is given 80 kbps. And the frames are sizes of 1000 bytes. L is 1000 bytes. Length of the acknowledgement is given. What is that? 100 bytes. And receiver side bandwidth is given, which is 8 kbps. TP is given 100 milliseconds and asking you to find out throughput. So simple, right? This you can calculate Tx, L by Bs, 8 into 10 power 3 by 80 into 10 power 3. This is coming to 0.1 second. Similarly, from these two you can calculate the TACK, which is LACK by BR, receiver side bandwidth. LACK is 100 bytes, which is 8 into 10 square by bandwidth at the receiver side 8 into 10 power 3. This is also 0.1 second. And this is in terms of millisecond, just convert this into seconds, which is getting 0.1 second. So therefore, what is the throughput formula? As it is stop and wait, so throughput of the stop and wait is equals to total data size by total time, and that this is clearly mentioning sender throughput. It is clearly mentioning sender throughput. Are you finding sender's throughput? So it means total data size. What is the total data size that you are having? The sender is pressing how much data? 1000 bytes of data. So 1000 by Tx 0.1 plus TACK 0.1 plus 2 into TP 2 into 0.1, that is equals to 10,000 by 4, which is 2500 bytes. This is bytes, no? And this is all in terms of seconds. So bytes per second, that's it. So bandwidth is given 128 into 10 power 3 bits per second. Packet size is given 1 kilobyte. One way propagation delay TP is given 150 milliseconds. And efficiency is given 100% efficiency. And asking you to find out number of bits in the frame sequence number field. From these two, Tx can be calculated L by B. Let's say this is 8 into 10 power 3 by 128 into 10 power 3. So 8000 by 128 milliseconds. What is it? So 8000 divided by 128, you are getting 62.5. So Tx is ready and Tp is ready. So Tp by Tx. Tp is 150 milliseconds by Tx is 62.5 milliseconds. So 150 by 62.5, which is 2.4. And the question is given efficiency is 100%. So because of this we have a condition. What is the condition? W is equals to 1 plus 2a. So 1 plus 2 into 2.4, which is 4.8. 4.8 plus 1, 5.8. This you can consider as 6. And you know that this is given selective repeat protocol. It is selective repeat. So in selective repeat, what is the window size? 2 power n by 2 is equals to 6. That implies 2 power n is equals to 12. So verify. For what value of n I can have 12 frames in the sense? 4 frames. So that is why n is equals to 4. So 4 bits is the answer for this question. Everybody is getting?